This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 55. Today's presentation is titled Satellite-Based TC Surveillance Since Katrina, an Exciting Era. The presenter is Jeff Hawkins, retired satellite meteorologist from the Naval Research Laboratory and consultant for NASA and Northrop Grumman. Our discussion after the presentation will be facilitated by Stephanie Stevenson, a meteorologist and programmer with the Technology and Science branch of the National Hurricane Center. Just a few reminders before we get started is that this session is being recorded, so if your colleagues are unable to join us due to shift work or other reasons, they will be able to find it on the VLab and YouTube later. There will be an opportunity for Q&A after the presentation, so please post your questions in the chat room and we will field them through there. We're always looking for future presenters, so if you have an application you'd like to share with your colleagues, please get in touch with us. We'd love to have you. And the training team can help create training materials that may be unavailable or point you to materials that you may be unaware of. Brian Mata and the Office of the Chief Learning Officer, as well as our cooperative institutes, can help regarding that. Just a few thank yous to our Tower S team, particularly Kashad Bowman and Lee Byerly, for their support behind the scenes, as well as the Office of the Chief Learning Officer, GOZAR, and JPSS. I'd also like to make just a few introductions, some new members to our satellite team here at headquarters. We had a student intern join us this week. Anthony Crespo will be with us this summer. He is a PhD student at UW-Madison. We also have a new addition to our Tower S team, V. Wegman, who is working on communications. So welcome to both of them. Without further ado, I'd like to introduce Jeff, who received his bachelor's and master's degree in meteorology from Florida State University and first worked for NOAA's Hurricane Research Division in Miami, flying their P3s to help validate NASA's SeaSat satellite and studying air-sea interactions. He took a job with the Naval Research Lab working on satellite oceanography applications, ocean fronts, and eddies via altimetry and mapping sea ice via passive microwave imagers and altimetry. In 1992, he transferred to NRL Monterey to get back into meteorology and focused on remote sensing applications related to tropical cyclones, ocean surface wind vectors, and many other topics. So Jeff, welcome to the Satellite Book Club.
Thank you, Jordan. I'd like to acknowledge my co-author, Chris Veldon, as well as the contributions that you'll see here from Derek Herndon, Tony Wimmers, and Tim Olander from SIMS, Buck Sampson from NRL Monterey, and John Naff from NOAA STAR in Fort Collins. So we're going to summarize very quickly the advancements, and then we're going to show you some examples for each of these. First, the global operations of advanced geostationary Viz, IR, and lightning imagers that most of you are very familiar with, GOZAR, MSG, Himawara, and the Chinese geostationary. The addition of low-frequency passive microwave sensor wind speeds, that is relatively new with regards to sensing maximum surface wind speeds. Upgraded LEO microwave sounders, the availability of near real-time synthetic aperture radar or SAR ocean surface winds, and demonstrations of SmallSats and CubeSats in the last few years for TC applications. And we'll talk a little bit about the maturing of automated algorithms to estimate tropical cyclone properties. A few limitations exist, and that is the lack of a sounder on the DoD follow-on called the weather sensor follow-on microwave to replace the SSMI sensors, and the lack of surface airborne truth for TC remote sensing algorithms outside of the North Atlantic. Most of us are very familiar with atmospheric motion vectors, AMVs, but with the GOZAR, we're able to see ultra-high spatial and temporal resolution AMV fields using a novel optical flow tracking methodology that enables AMV production in a tropical cyclone's cold central dense overcast or CDO region where conventional AMV techniques can struggle. So the example provided by Chris here shows the wealth of AMVs that potentially can be produced. In the last summer season, there has been good agreement with co-located high-level G4 flight level data, as well as dropsondes in the North Atlantic for last summer's successful demonstration. And there are data assimilation activities underway with hurricane modeling partners such as HWRF to assimilate these winds. SIMS is in the process of readying this product for transition to operations at NOAA NESDIS, and there are plans to extend the processing methodologies to GOES 17 in the Eastern Pacific and possibly Himawara 8 and 9 to cover the Westpac. Focusing on IR, many of you are familiar with the Dvorak method. In this case, we're going to talk about the advanced Dvorak method that Tim Olander has headed. It utilizes improved IR imagery from new generation geostationary satellites to produce objective and fully automated intensity estimates, and now includes the use of passive microwave imagery, which has significantly enhanced the performance in the central dense overcast stage, or CDO stage, that has been a problematic area for Dvorak since its formulation many years ago. The ADT has been expanded to the application of subtropical and extratropical transition storms to fill in the gap, and employs now the automated storm centering technique, Archer, which greatly enhances the capability across the global domain. It is now used routinely as an operational tool at global TC forecast centers such as NHC and JTWC, but also others around the world. Tim and company, along with Tony Wimmers, are now employing AI machine learning techniques to enhance information for the advanced Dvorak technique. So the ADT objectively interrogates satellite imagery and stores environmental and analysis parameter in what they call a storm history file. So the question was asked, can a deep learning model use the ADT history file parameters to derive improved performance, especially in those cases where the ADT struggles? So in this case, the final model that they formulated was a fully connected artificial neural network, regression-based loss function. It utilizes 26 input ADT history file features shown in the chart on the right. It has one hidden layer with 32 neurons and one output layer with a single maximum surface wind speed value as the final output. Using multiple years of training data, as well as multiple separate years for validation, and then 2 years, 2017 and 2018, for independent test data, we can see, as highlighted in the lower right in yellow, that the AI version of ADT outperforms the current operational algorithm using a year of independent test data. Also in the IR framework, John Naff and company have, since Katrina, developed methods to estimate TC wind radii. So we're talking gale force, 50 knot, and hurricane force wind radii from geostationary IR imagery to form global size climatologies. So on the right-hand side, you can see these for the various tropical basins. And basically, with that information in hand, we can now, in near real time, provide estimates of these wind radii from, for instance, SAB or TAFB, as well as the best track. So this provides important information on the wind radii in near real time. We also have a satellite-based consensus, or SATCON approach, that has matured and is used routinely operationally at TC forecast centers. So satellite consensus back in the 2005 or Katrina timeframe consisted of what was called the AODT, as well as AMSU, both from SIMS and CIRA, and now has matured in the 2021 timeframe to include the ADT and multiple microwave sounder estimates of TC intensity. So this is AMSU, SSMIS, and ATMS. So the validation that you see here is against recon-aided best track. In other words, when we had aircraft recon data available that was used to, in essence, generate a best track value that is highly confident. So you can readily see that the bias, the mean error, and the root mean square error has been reduced significantly from 2005 to 2021 to the values that you see here with an RMSE of approximately 9 knots. New SATCON members are being developed and assessed as we speak, and we'll talk about SMAP. DAV is another IR method, the AIDT that we just talked about, the deep micronet we'll talk about in a moment, and TROPICS. So Tony Wimmers has been utilizing deep learning to basically process passive microwave imagery to come up with a maximum surface wind speed or intensity estimate. With that in mind, I focus on the right side of this graphic to show that the model estimated maximum surface wind is on the vertical axis, the best track is on the horizontal axis. And you can see that the one-to-one correlation is quite good. The RMSE is on the order of 10.6 knots. And this has shown significant improvement over other methods that have been used in the last 5 to 7 years with regards to leveraging the microwave data, the imager data, not the sounder data, to come up with a tropical cyclone intensity estimate. On the other hand, one of the things that we've lacked is the use of or availability of near real-time maximum surface wind speed estimates. So we've used, for instance, scatterometers at the lower end of the spectrum, but in this case, we now have L-band or 1.4 gigahertz microwave imagers on the LEO satellites with very large antennas whose purpose was something other than tropical cyclone remote sensing. And the two here are the soil moisture active passive sensor or SMAP and the soil moisture and ocean salinity sensor, SMOS. So these are two NASA sensors that are available in near real time. The 1.4 gigahertz is not impacted by rain, and thus we're able to extract estimates of maximum surface wind speeds in near real time. This chart provided by Paul Chang basically shows the flyout chart for scatterometers. Note that we have many scatterometers from China, and as we well know, that data is not available in near real time to be utilized by US government. Therefore, we're basically looking at those scatterometers from EUMETSAT, as well as India and a few other companies or entities that are available in near real time. The next one is OceanSat 3, the green one that you see at the bottom here, that will be launched in the near future. In the past, synthetic aperture radar data was not available in near real time or was very costly. But more recently, SAR sensor data sets such as Sentinel with a data latency of 2 hours and RadarSat with a data latency of 8 hours are now available over targeted TCs in coordination with multiple agencies. These SAR winds enable extraction of tropical cyclone maximum wind speed estimates due to very high spatial resolution and minimal rain pack, and this graphic is courtesy of Buck Sampson at NRL Monterey. So now that we have a combination of multiple scatterometers, the L-band radiometers that we showed a moment ago, multi-band radiometers such as AMSR2 and the upcoming AMSR3, and the cross-polarized SARs, how do we, in essence, blend that information together to come up with wind radii and a wind field? So this is an effort by John Naff and company called the Multi-Satellite Platform Tropical Cyclone Surface Wind Analysis that is produced every 3 hours that basically combines the data sets from these both passive and active sensors to come up with a automated product to generate a surface wind field for TCs around the globe. In the SmallSat and CubeSat demonstration realm, we have Cygnus, the Cyclone Global Navigational Satellite System, which is a joint University of Michigan and NASA effort, launched in 2016. It's a constellation of 8 SmallSats and a 35-degree inclination, receives the GNSS signals bouncing off the ocean surface to retrieve accurate surface wind speeds not impacted by rain. Tempest-D is a joint effort by Colorado State University and NASA JPL. It's a CubeSat water vapor profiler launched in 2018, and it's a tech demo of a low-cost LEO microwave sounder with very good NE delta T and long-term operations. Basically a water vapor sounder, not a temperature sounder. And we have launching tomorrow the Pathfinder for Tropics. And so this is a joint effort between MIT, Bill Blackwell and Company, and NASA. It's an innovative low-cost solution to provide high temporal sampling of temperature, moisture, and precipitation from LEO using frequencies in the F and the G band. So this will consist of a constellation of 6 3U CubeSats. The Pathfinder launch is actually slated to be on a SpaceX satellite tomorrow, and there will be 2 satellite launches in the first half of 2022 to put the constellation of 6 satellites up early next year. So in summary, we have a geostationary global ring of advanced spectral, spatial, and temporal imaging, resolution, and lightning mapping observations. We now have advanced LEO microwave sounders, such as that on JPSS with the ATMS. We have enhanced mapping of high tropical cyclone surface winds with SMAP, SMOS, and SAR. And we have promising SmallSat CubeSat demonstrations, such as we talked about with Cygnus, Tempest-D. I did not talk about RainCube. We have a number of other satellites, as well as future SmallSats and CubeSats. So TROPICS is going up, the first one tomorrow. COVAR, which is basically a WindSat-like device, will be going up fall of this year. And Care Weather, which is a private company, is working on a CubeSat scatterometer with a hopeful launch in the 2023 timeframe. So we have advanced maturing and validated algorithms for automated extraction of TC, which was not really available much in the 2005 timeframe. So I'm going to summarize now the role of SmallSats and CubeSats. To date, we've seen private industry and some government R&D funding, but there has been an explosion in communication and imaging constellations that were really never thought of 15 years ago. So many of you are familiar with Starlink, and then we have the Amazon version, OneWeb, Dove. So these are communication and imaging constellations that are rapidly coming online because of engineering maturation and component advances, whether it be the space bus, receivers, LNAs, etc. And we've seen very successful demos such as Tempest-D and RainCube. And this is basically brought on by a global buy-in and what I would call a race to innovate. So everyone has a chance to carve out their niche and creatively move forward. So in the near future, as I mentioned, tomorrow, the Pathfinder for Tropics will be launched, the constellation the first half of 2022. The second version of Tempest-D will be launched along with COVAR in the fall of this year to the International Space Station, and Care Weather will launch a CubeSat C-band scatterometer, hopefully in the 2023 timeframe. So the opportunities here that it has leveraged lessons learned and technology innovation to build high-performance tropical cyclone monitoring platforms with high temporal sampling, i.e. constellations. And if we could remove the cost constraints, such as on tropics, we could see, for instance, a 50% or more reduction in NE delta T, which would give us the sensitivity that we need, for instance, for things like tropical cyclone warm core analysis better. There's also the potential for deployable antennas, which basically would mitigate the small inherent size that's available on CubeSats today. In the future, The obvious question is, what is the right mix of weather and/or TC satellite platforms and sensors in the 2030 timeframe? So we have our legacy sensors that are very long-lived, excellent capabilities, but very costly. And now we have SmallSats and CubeSats, low cost, rapid innovation, high temporal samplings, but with typically poorer sensitivity depending on multiple factors. So in essence, the summary here is the next 15 years could represent a radical revolution in space-based weather and TC monitoring capabilities. So with that, I'll end and be glad to take any questions. Thank you.
All right, thank you, Jeff. I want to encourage everyone to stay on for the discussion and complete the survey that will be posted in the chat room shortly. A reminder, a week from today on Thursday, July 1st at noon, same time, noon Eastern time, Randy Loganbaugh, a researcher from Sandia National Laboratories, will be discussing the geostationary lightning mapper observations of bright meteors. So we hope you tune in for that. I want to also encourage attendees to contact the Tower S team, Lee Byerly or Kashad Bowman, for questions about the Satellite Book Club or for satellite configurations. More information will follow in an email from Tower S. So we'll go ahead and proceed into the discussion. For the attendees, you can insert your questions into the chat room or indicate if you would like to verbally speak up. And while we're waiting for questions to roll in, I'll go ahead and start, Jeff, with this one. What are some of the cost comparisons between the legacy platforms and satellites, sensors, and the SmallSat CubeSats that you were talking about?
So the rough ballpark comparison is the following. So a typical microwave sounder cost, such as ATMS, is anywhere from 100 million to 150 million per unit. For instance, the TROPICS CubeSat microwave sounder, once it's built, i.e. once the design is made, is probably on the order of $2 million a unit. So you can see that there's 2 orders of magnitude difference between the CubeSat and the legacy sensor. However, there are significant differences between the performance, especially in terms of, for instance, sampling the warm core that is the essence of what the microwave sounder can do for tropical cyclone intensity. So as I noted, there are ways to enhance the sensitivity, for instance, of a TROPICS-like CubeSat microwave sounder. So there are a number of methods, advances that can be done, realizing that TROPICS was a cost cap mission. And so we could basically fly a SmallSat CubeSat microwave sounder that, for instance, costs probably in the neighborhood of 4 or 5 million. That would have very good capabilities. And with a constellation of that, then the temporal sampling would be greatly enhanced.
All right, looks like we have a question coming from Jack Bevan at the Hurricane Center. Can you please comment on specifics of upcoming low frequency microwave imagery, particularly 37 gigahertz? What is the current launch schedule for such instruments?
So 37 gigahertz, the next launch would be the Weather System Follow-On, which is the DMSP follow-on, so to speak. So that the latest date that I have for that is probably in the 2023, 2024 timeframe. And then there would be a second WSF M for microwave, probably in the 2028, 2029 timeframe. There would also be 37 gigahertz on AMSR 3, which will be launched likely in the next couple of years. So there will be some new launches available for that frequency.
All right, another question. How can TC analysts and warning centers deal with the increasing volume of digital satellite data sets from both GEO and LEO sensors across their large areas of responsibility?
So I love that question. You know, before GOES-R, I can remember many of the conversations dealing with GOES-R and JPSS, 15, 20 years ago, and how are we going to deal with the volume, which we just at the time had very little clue on how that was all going to come about. But due to the maturity of computer processing and data storage, and as I noted, the automated algorithms that are available today. So whether it's ADT or SATCON or the various algorithms, for instance, that John Naff and company have generated to analyze surface wind fields or 3D wind fields, it has become commonplace for these products to be available in near real time, i.e. within, in some cases, tens of minutes, other cases within an hour or 90 minutes, such that the Tropical Cyclone Warning Center can utilize those products within the warning cycle process, which has extreme time constraints.
I'll just mention from the NHC side, we actually got our AWIPs configured to see SAR imagery this season. So this will be our first year. We'll be pulling that in real time for forecasters to analyze alongside all the GOES imagery and everything else that they look at. So we're pretty excited about that.
It's my understanding after talking with Josh Casas that ONR basically has helped to implement the NRLTC microwave products in-house at NHC. So that is a great step forward in terms of removing dependence on outside products and also potentially speeding up the delivery of those products and also hosting them obviously on an in-house software platform.
Yes, I think that's a work in progress right now, but we're getting close to having that ready for us to use.
Understand.
We have a question from Michael Jamakowski. Did you or Chris participate in any of the GeoXO concept development meetings to make recommendations on the TC surveillance for GeoXO? If not, what would you recommend? And GeoXO is the future GOES satellite series.
The answer is I did not participate on the GEO side of the thing. I did participate on the LEO side of the thing. So in my role as a consultant with Northrop Grumman, we did work on a 6-month project that looked at what would be our recommendation for IR and microwave sounders as well as radio occultation or RO sensors for the 2030 timeframe. So in that context, we came up with a suite of IR and microwave sounders and RO that we thought best fit the bill. And one of the topics of consideration was tropical cyclone monitoring, but as you might expect, NWP data assimilation was at the top of the list. In terms of geostationary, I think we've seen with GOES-R that the combination of the multispectral channels that we have, the sensitivity, as well as the scanning regimes has been greatly augmented from the previous GOES constellation. I think in general that the automated algorithms that we've seen, that we noted here in the presentation and more to come, that the advent of AI and deep learning has basically pushed those algorithms to a new level. And with that in mind, has squeezed out additional precision that was not available with the normal, what I'll say is regression-based analysis.
Okay, well, we're talking about geostationary satellites. GOES-R has been around for a few years now. Do you think the tropical cyclone community is getting everything it can from all the advancements that came with the GOES-R series? or do you see areas where improvement could possibly be made?
I'm sure there are. I'm not a geostationary expert, so I'll basically leave that to a couple of other folks at, for instance, Sims and Sarah, who have basically spent their life working in that realm. The combination of channels, and as you saw in the context of the AMVs, the optical flow technique has shown significant promise, and as noted in the slide today, that is getting close to operations. And once that is in operations, then the ability to fine-tune the assimilation of those winds along with the current AMBs that we have, I think that you'll see some potential enhancements in NWP, as well as near real-time analysis of, for instance, upper level wind fields, and understanding of when you have, for instance, outflow jets, whether they're turning on or turning off, that have direct impacts on TC intensity.
Okay. Matt Gunshore put in the chat that on the GeoImager side, I think he's talking about the future GeoXO will have very similar IR bands to what is on ADI. So if people have ideas about scanning strategies, whether you want 2 mesos or 2-minute CONUS or something else, they should bring those ideas up to Jordan or mention them in the chat room here so that we can start researching different things in the future. Looks like we just got another question from Jordan Girth. Has the VIIRS day-night band contributed to any of the tropical analysis and forecasting improvements? Is there any possibility of a day-night band AMV once JPSS and NOAA 21 is launched?
So the answer is yes. The day-night band has proven that it can greatly assist tropical cyclone monitoring. So for instance, there have been a number of papers published to illustrate how the day-night band can mitigate the fact that we're typically reliant on both long and mid-wave IR at night have obvious limitations, and the day-night band can see exposed low-level circulations or mid-level circulations that can produce not only relocated or more accurately located tropical cyclone center locations, but that has a direct impact on the Dvorak or intensity estimate. And for instance, the CPHC has had several instances where DMB data was crucial to relocating and changing the intensity of TCs in near real time. So with that in mind, there are a number of efforts both on the geo side and the LEO side to include day-night band channel on future sensors. So it's a burgeoning field. So I thank Steve Miller and his team with regards to exploiting the DNB for a wide variety of applications, not just for TC monitoring.
Okay, we have another question here from Rudolph Williams. With the new ASCAT products being planned and coming out soon, do you think these will help close the gap in some of the misses we see during TC development? Or do you think there's something else that could be improved that could help with their accuracies?
The answer is yes. So the new UMETSAT scatterometer will have a 30% wider swath. So instead of 500 kilometers on each side, will be on the order of 660 kilometers. So there'll still be a gap in the middle. The interesting aspect, and I noted on one slide that a private company is proposing a C-band CubeSat scatterometer. And if that actually comes to fruition, the potential of having a scatterometer constellation in a CubeSat form factor means that we could have high temporal sampling from a C-band scatterometer with something on the order of 25 to 30 kilometer resolution that would potentially greatly aid the tropical cyclone and the marine meteorology community.
Okay, not seeing any questions at the moment. Jack did note earlier that they announced that the TROPICS has been delayed or postponed from tomorrow, Monday at the earliest now. So unfortunate news there, but hopefully it gets up soon.
I think I can wait a couple more days. So this has been something on the order of 6-7 years in the making, and we're looking forward to the full constellation being launched next year.
Yeah, from the technology side, all of these new instruments are great resources for tropical cyclones, but I'm thinking about configuring, getting all of these in front of the forecasters, and lots of data coming in with all these new technologies, lots of things to work through.
So as you noted, in order to, for instance, answer one of the questions earlier was how do you handle the wealth of data that's coming in? So you need to be able to incorporate, each of these new capabilities either into existing products where hopefully these new sensors are adding value, and or deriving new products that replace something old that has either higher precision or new capabilities that are addressing specific user needs.
All right, looks like one last question here from Joe Zajac. What do you think the effect will be of these new resources on the tropical forecasting business as perceived by the layman?
As perceived by what?
The layman? Just
by the layman. Okay. I think it all boils down to, what is the final accuracy? What is the final accuracy of the message that the forecasters put out? In other words, if the layman or the casual user sees improvement, then they're obviously going to look at that in a positive light. If they, for some reason, perceive that the forecast or the advisories that they're getting have degraded for whatever reason, then obviously there's a negative perception. But I don't see that happening. I think the wealth of potential new sensors and capabilities that are coming online have the potential to significantly enhance our current capabilities. So in that light, I also see that the legacy sensors, in light of the technology revolution, are going to get, in the satellite world, we call it size, weight, and power, so SWaP. So the SWaP is decreasing, i.e. the costs are decreasing for these legacy sensors. So even the JPSS sensors, their cost is going to decline in the next 10 to 15 years. And that's being driven in part by the revolution in the technology that is enabling, for instance, CubeSat sensors to exist. So I think it's good news all around, and I have a very positive feeling for the overall impact.
all right. Thank you, Jeff. I think I'll toss it back to Jordan now for some final remarks.
Okay, thank you, Stephanie, and thank you, Jeff, for that great presentation. Also, thanks for everybody joining us today. We had over 100 participants, so that was absolutely fantastic. As Stephanie already mentioned, we'll be continuing our Satellite Book Club Seminar Series next Thursday, July 1st at 12 noon Eastern Time. Randy Longenbaugh will be talking about geostationary lightning map observations of bright meteors. So just in time for the 4th of July. And as always, if you have any questions related to satellite data, please feel free to get in touch with our TowerS team. You see the information there. I will just say on behalf of the National Weather Service Office Observations, we are looking towards possible future missions for LEO, particularly scatterometer. So it is on our horizon to continue to improve our observations of tropical cyclones and other phenomena that support tropical forecasting, and quite frankly, all of our ocean basins. So with that, hope you stay well, hope your summer's off to a good start, and you'll be able to join us next week. Until then, take care.